In section 6.1, we're going to look at inverse functions. Inverse functions come up a lot in trigonometry, so that would be our Math 140. But first of all, before we even talk about inverse functions, we have to talk about what it means to be what we call a one-to-one function. And a one-to-one function means that, and we'll look at the definition here, that if you take any a and b from the domain of our function, so these are x values, so take any x values, and if these x values are different, that means the corresponding y values have to be different. So this means it is one-to-one if x values different, corresponding y values different. Another way to say that is, okay, well, let's say that the y values are the same. That means the corresponding x values will also have to be the same. I know looking at definitions is a little bit abstract, so we're going to go through a concrete example of how you're going to use this definition. But I also want to look at what's called a horizontal line test. So if you have a function, it passes vertical line test, meaning any vertical line will pass through at most one point on the graph. If a function is one-to-one, it will also pass a horizontal line test, which just means that any horizontal line will pass through the graph at most once. So a one-to-one function has to pass both vertical line tests and horizontal line tests. So we have our definition, and we have what it means to be a one-to-one function with the graph as well. Now, looking back at this definition, if you know that your function is not one-to-one, then you would actually use this first version, where the a is not equal to the b. So if you want to show not one-to-one, you use the first version. The alternate version would be if you want to show one-to-one. And I know it means nothing right now until we look at an example. So in example 1a, we want to use both the definition and we're also going to graph to show whether the function is one-to-one. Now I know looking at f of x equal to x squared minus 1, I know that that's a parabola, it's opening up, definitely not going to pass the horizontal line test. So I already know by imagining the graph that it's not one-to-one. So I already know that I'm going to use the first version. Sometimes, if you don't know whether a function is one-to-one or not, it's best to actually graph it first. So let's go ahead and graph f of x equal to x squared minus 1. So again, that's a parabola opening up, and the minus 1 means we're just going to shift it down 1. So it's going to pass through 0, negative 1, 1, 0, negative 1, 0. Let's see, if I put in 2, I get back 3. Negative 2 gives me positive 3. And I have my parabola. Notice that if I draw any horizontal line above the vertex, it's passing through 2 points. So I've just shown by a graph that this is not one-to-one. That means if I'm going to use a definition to also show that it's not one-to-one, I'm going to use that first version. So what the first version says is x is different means y's are different. That means one-to-one. So not one-to-one means x is different, y's are the same. So all I have to do is come up with one example where the x values are different, but the corresponding y values are the same. And there are infinitely many to choose from. So let's let a equal 1 and b equal negative 1. So clearly 1 is not equal to negative 1. So I have two x values that are not the same. However, if we look at the corresponding y values, f of 1 is equal to 0. F of negative 1 is also equal to 0. So f of 1 is equal to f of negative 1. So remember, in order for a function to be one-to-one, if the x's are different, the y values will also have to be different, but these are the same. So we have shown algebraically by the definition that this is not one-to-one. Let's try that again with another function. In part B, we have f of x equal to 2x minus 3. I know that graph is going to be a slanted line. And in fact, I know that it will pass the horizontal line test. So I know it is 1-to-1. I can go ahead and use the alternate version to show 1-to-1. But again, if you're not sure, graph the function first. So let's graph, why don't we make a table of values? X and Y. And I think I'll start with 0 because that's always nice. If X is 0, Y is -3. If X is 1, Y is -1, 1, -1. Can't add. 2 gives me 1. Let's graph those points. 0, -3, 1, -1, and 2, 1. Okay, they all line up. And I have my line. I can see that, yes, this does pass the horizontal line test. No matter where I draw a horizontal line, it'll pass through at most 1 point. So is 1-to-1. That means I'm using the alternate version. So not 1-to-1, all you have to do is come up with one example where x's are different, y's are the same. However, it's a little bit difficult if you're showing is 1-to-1. Is 1-to-1 means that for any x values in the domain, you must have that if the y values are the same, the corresponding x values are also the same. So we're not putting in particular numbers because we have to show it works for every number. It's impossible to check every number in the domain. So we're just going to go ahead and start out with f of a equal to f of b. So let's just suppose that we have these y values that are the same. Now we just have to show that the corresponding x values, which are a and are b, they're also the same. But I'm not putting in numbers because I have to show it's true for all x values. So I'm going to leave a generic a and a generic b that will stand for any value in the domain. Now we know that f of x is equal to 2x minus 3. So if I just rewrite f of a as 2a minus 3 and f of b as 2b minus 3, then maybe I can use algebra to get down to a equal to b. And I can. If I add 3 to both sides, we get 2a equal to 2b. And if I divide by 2 on both sides, I get a is equal to b. So we've just shown that we have y values that are the same, gives us x values that are the same, and this is true for any a and b in the domain. Thus, we have f is 1-to-1. And I know that is abstract, so just let it simmer for a bit and we'll look at some other stuff with inverse functions. Okay, so we talked about a function being 1-to-1. If a function is 1-to-1, then it's going to have an inverse. And inverses are very important. They undo each other. So for example, if I have some function f, and here is its domain, and I have some x in the domain, it's going to take that x and it's going to give back a y in its range. Well, its inverse will take that y value, and I'm going to call the inverse g. So if g is an inverse of f, it's going to take that y value and it's going to bring it right back. So that x value that we initially put in remains unchanged. They undo each other. Formally, how we say that is that if f is 1-to-1, then g is going to be the inverse function of f, and f is going to be the inverse function of g. They're inverses of each other if, when you compose them, so remember this is not multiplication, this is composition. So it's f of g of x. So you're going to put an x into f of g, and you're going to get back that same x. It remains unchanged. And you have to compose them in both directions. So you also have to check g of f of x is also equal to x. Now let's try out that definition. Example 2. We want to check to see if g and f are inverses of one another. So all we have to do is compose them in both directions. Let me do f of g first. So we're going to put in an x value, and we should get that x value back. So remember, this is f of g of x. We want to go ahead and figure out what g of x is and put it into our function f, but we already know what g of x is. G of x is 2x minus 1. So now wherever we see x in our function f, we just replace it with 2x minus 1. This is going to be 1/2 parentheses 2x minus 1 plus 1/2. So again, all we did was replace x with 2x minus 1 in the definition of our function f. Let's go ahead and distribute that 1/2 to get x minus 1/2 plus 1/2. And then the negative 1/2, positive 1/2 cancel each other out. So what that says is I put in an x, I got back the x. But we have to do it in both directions. So now let's check g of f of x, which is g of, we're putting in f of x into g. So that's g of f of x is 1/2 x plus 1/2. That means wherever we see x in g, so 2x is going to be 1/2 x plus 1/2. So wherever we see x in g, we replace it with 1/2 x plus 1/2. And then we have our minus 1. Distributing the 2, this becomes x plus 1, and then we have our minus 1. And we're done. We composed in both directions. We put in an x, we got back an x. So yes, that would be my conclusion. Just showing this is not enough. You have to make a conclusion. So yes, they are inverses. So when a function does have an inverse, we're going to use this notation that may be a little bit confusing, and that would be in the red here. It says notation. The inverse of f is written as f, and you see that negative 1? It looks like an exponent, but it's not. That is inverse notation. That actually reads f inverse, not f of negative 1. Okay, so it's not the exponent negative 1. If you wanted to write a function to the exponent negative 1, this is how you would do it. So first of all, f, and we have this negative 1 of x, that's an inverse. If I write f of x, and then I put the negative 1 on the outside, that's exponent. It's very subtle and it can be confusing. So oftentimes, if we want to talk about a function to the negative 1 exponent, we actually prefer to write it as 1 over f of x, because that takes away any confusion. So if you do have a one-to-one function, it's going to have an inverse. How do you find the inverse? Well, it's very simple. All you do is you just exchange the x and y values in the equation, and then you solve that equation for y. Once you have the y by itself on one side of the equal sign, you just replace it with the inverse notation. Let's practice this with example 3. So example 3, we have this function, f of x equal to 1 over x plus 3, and it's 1 to 1. So I know it has an inverse. So if I want to find f inverse, then all I have to do is exchange my x and y's. So first thing you want to do is just replace your f of x with y. So you can exchange x and y. This becomes x equal to 1 over y plus 3. Now that I've exchanged x's and y's, I'm going to solve this equation for y. So I think I'm going to clear the fraction by multiplying both sides by y plus 3. And then it will cancel on the right-hand side. So I get y plus 3, and I'm not going to distribute the x equal to 1. Because I want to get the y by itself, I can at this point simply divide by x on both sides. And you see that these x's will cancel on the left, so that I have y plus 3 equal to 1 over x. And now all I have to do is minus 3 from both sides. So last thing we do is we replace the y with the function, or the inverse function notation, to get f inverse of x equal to 1 over x minus 3. And that's how you find the inverse function. Exchange x and y, solve for y, write with inverse notation. It should be noted that if you would like, you can also combine this into one fraction as 1 minus 3x over x. I don't think MyLab will be picky about that. So the next thing I want to talk about is the relationship between inverses and their graphs. So when you look at the graph of an inverse, they're going to be reflections across the line y equal to x. So y equal to x is going to be our axis of symmetry. Okay, and then another property that we get, and this is really important, that if you have some point AB and it's on the function f, then if you flip them, BA is a point on its inverse. And that makes sense because remember when we were finding the inverse of the function, we exchanged the x's and the y's. So if you have a point xy on your function, yx is going to be on its inverse. Now, looking at this in a larger picture, think about what we're doing when we exchange x and y values. Your x values are the domain, y values are the range. So if you have a function with a domain and a range, and you switch them, then the inverse, its domain will be the function's range, and its range will be the function's domain. You're switching domain and range. Regardless, let's look at example 4. We're going to graph the inverse function of the function that we have on this graph, but we don't have the function, we just have the graph. So remember, we do have our axis of symmetry, and our axis of symmetry is going to be the line y equal to x. So y equal to x is just a diagonal line that goes to the origin, like so. So again, this is our axis of symmetry. And what that means is our function here in red is going to have to reflect across that line. I'm going to add arrows on the end. Let's pretend like this goes on forever and ever. I'm going to use that second bullet. Notice that my function, now let's look at some really nice points. Let's see, 1, 2, I have 3 really nice points on my graph. This first one is going to be 1, 2, 3, comma 1. And then I have 1 comma 0. And it looks like negative 1, 1, 2, negative 3. So I have these 3 points on my graph of f. Let me just write that as a table of values, x and y. So we had 3, 1, 1, 0, and negative 1, negative 3. That much must mean that the inverse function, f inverse, is going to pass through, exchange x and y, 3, 1 becomes 1, 3, 1, 0 becomes 0, 1, negative 1, negative 3 becomes negative 3, negative 1. It's that simple. Once you have points on your function, exchange the x and y, and now you have the points on your inverse function. Let's go ahead and graph the inverse function. It's going to pass through the point 1, 3. Let's see, 1, 2, 3. It's going to pass through the point 0, 1. And it's going to pass through negative 3, 1, 2, 3, negative 1. So if I connect these lines, you could see that it's a reflection of this graph. Now, when we say reflect, what we mean is that if you pick a point on F, it's going to be the same distance away as the point across the axis of symmetry on F inverse. So if you look at the point 3, 1, it's going to pass through 1, 3, and those points are the same distance away from our axis of symmetry. Let's look at negative 1, negative 3, and yes, those points are the same distance away on opposite sides of our axis of symmetry. So now all I have to do is finish off the graph. I can just look at F to know that F inverse is going to keep going up. And typically, if you have two graphs on the same coordinate system, you should label each one. And then I can see that at the bottom, this is just going to continue down. And that's it. That's how you graph. Given the graph of an inverse, find some nice points. And even if there's not nice points, you can kind of guesstimate and then switch the points, graph your inverse function. The last thing we want to do is we want to put all these ideas together. Example 5, we have a one-to-one function f. We're going to find the inverse, and then we're going to graph both functions on the given graph. So first of all, I want to find my inverse function. So I'm going to replace f of x with y. And then once I've done that, I'm going to exchange my x and my y to get x equal to negative 3y plus 5. And now I am going to solve for y. I think I'm going to add 3y to both sides so that it's positive. It doesn't really matter the order that you solve for y. And then I'll go ahead and minus x from both sides. And divide by 3 to get 5 minus x over 3. Finally, I'm going to replace y with the inverse notation, f inverse of x. That would be equal to 5 minus x over 3. So we have found our inverse function, and we want to graph both on this given graph here. Well, remember, I only have to graph one and then flipped the points, and I'll get the graph of the other. So why don't I just go ahead and graph f? Maybe I'll put some points down here. I'm going to put f in red. I see that it's a line. Let's go back to that. Let's see. We'll start with 0. So if I put in 0 for x, I get 5 for y. If I put in 1 for x, I get 2 for y. Let's do one more. If I put in 2 for x, I have negative 1. Let's see what those points look like. So we have 0, 5, 1, 2, and 2, -1. Do those line up? Yes, they do. Maybe I'll do one more. If I put in 3, I get back 4, or -4, sorry. 3, -4. Okay, yes, that looks like a line. Kind of sad line that I'm drawing. That's okay. This is our function f, and I'll label it down here. Okay, so let me go ahead and get some points for f inverse. Again, I don't have to plug it into the function. All I have to do is take the points that I have for f and switch them. So I have 5, 0, 2, 1, -1, 2, and -4, 3. Let's go ahead and graph those. 5, 0, 2, 1, -1, 2, -4, 3. And those do line up. So this would be my graph of f inverse. And we could see if we looked at our axis of symmetry, y equal to x, did these graphs do kind of flip across that axis of symmetry? So again, if you pick any point on f, you'll find its pair same distance away from that axis of symmetry. One last. In this last example, my function is the square root of x plus 4. And here I'm told that x has to be greater than or equal to -4. And I know that that's its domain, because notice that if x is smaller than -4, say -5, I'll have a negative underneath my square root, so it's not defined. Well, first of all, if I were going to find my inverse function, my f of x is y. Now, for now, I'm just going to put a comma and remind myself that the x values are greater than or equal to -4. Exchange x and y to get x equal to the square root of y plus 4. And then now this is important. To get that y out from underneath the square root, I'm going to have to square both sides. So recall that whenever you square both sides, you're making things bigger. You could end up with values that don't work, which is why I have that x greater than or equal to -4 there. Okay, so remember, we did exchange x and y's. So we also exchanged x and y with the x greater than or equal to -4. That's actually y values greater than or equal to -4, and I'll show you what that means later. Regardless, let's keep going and solving. If I square both sides, this becomes x squared equal to y plus 4. And then if I minus 4 from both sides, I get x squared minus 4 is equal to y. And I kind of don't like that order. So I'm going to change it to y equal to x squared minus 4. So this is a parabola opening up, shifted down 4. And we've already seen that parabolas are not one-to-one. They don't pass horizontal line tests. So although my function f was one-to-one, I now have this function that's not one-to-one. Let's keep going. We'll replace y with f inverse of x. And then we'll talk about the restriction on my x values in just a bit. Before we go further, I would like to go ahead and look at the graph of the function f. So my function f, and I'll make some values. I already know what the square root function looks like, and I know that the plus 4 means I'm going to shift to the left 4. So let's go ahead and start with that x value that we were given. Remember, x is greater than or equal to -4, so I'm going to start at -4. and I'll get 0. If I put in -3, I'll get 1. And I think the next nice value would be putting in 0, because then I'll have the square root of 4, which I know is 2. So how do I get 3? I need a 5 plus 4. I need a 9 underneath the square root. So I'm going to look at x equal to 5. Square root of 9 is going to be 3. And then I'll look at f inverse. And I'll change those points to 0, -4, 1, -3, 2, 0, 3, 5. I'm going to go ahead and graph these. My function f is going to be passing through -4, 0, -3, 1, 0, 2, and 5, 3. And then my inverse function is going to pass through 0, -4, 1, -3, 2, 0, 3, 5. So the graph makes sense, but the equation doesn't, because the equation of my inverse function says that it's a parabola, and I only have half the parabola. And that's because I have to restrict my x values. If we look at the inverse function, the largest x value is an x value of 0. Look at this first point. This is the point 0, -4. And 0, or smallest x value, sorry. So 0 is my smallest x value. The other x values are greater than or equal to 0. And that is important, because without that, that inverse function becomes a full parabola, and it's no longer one-to-one, and in fact, it's no longer the inverse function. So here we're putting together the graph with the function to get the correct inverse function. And this actually makes sense. Let's go ahead and go back to the graph, and let's look at this graph. Look at f. It starts out at the point -4, 0. So the smallest x value is -4. If you look at the domain of f, it's going to go from -4 to positive infinity, going back to the graph. So x value, smallest x value is -4, and then it goes to positive infinity. But look at the range. The smallest y value is 0. So the range of my function f is 0 to infinity. And when we exchange x and y values, we exchange domain and range. So my inverse function, the smallest x value is 0, and then it goes to infinity. So that would be the domain of f inverse. It's going to go from 0 to infinity. And then if we look at the range of the inverse function, those are our y values. Smallest y value is -4, and then they go up to positive infinity. So looking at the domain and range side by side, you can see that for my function f, domain -4 to infinity, range 0 to infinity. Switch those, and now the range of f becomes the domain of its inverse, and the domain of f becomes the range of its inverse. Okay, so that's it for this section.